So, the next lecture of discussion in this course of rapid manufacturing, we will see the topic on beam deposition processes. So, as it is very clearly says, there is a beam. So, this beam can be made of light, which can convert into heat, we can use it, or we can use a electron as a beam, and we can do it. We can use a plasma as a beam, and then we can do it. So, it is nothing but a source which can be light, which can be electron source, it can be a plasma source. So, we use these sources wherein which we have a focused thing called as beam. So, this beam is allowed to help in depositing on the surface through which we try to make a prototype or we try to make a rapid manufacturing part. So, the beam can be light, if you want I can change it, I will put it as photon. You can use photon as a source, you can use electron as a source, you can use plasma as a source. Why not use ion? Ion also can be used. So, you can use any of these sources, and all these sources when it strikes the material or matter, it tries to interact, and when it interacts, it tries to generate heat. We choose in such a way that it generates heat rather than transmitting. So, it generates heat. This heat will be used for sintering or melting, and you try to get the required output. So, this is what will be in a nutshell covered in this lecture. So, the content of this lecture, we will have a small introduction, followed by it beam deposition process we will see, material delivery system, wire feeding, we will see beam deposition system, and then we will try to see the process parameters, then process structure and property relationship, and finally, we will see beam deposition benefits and its drawback. Beam deposition process enables the creation of part by melting and deposition of material from powder or wire feed stock. So, you can make a powder or you can make a wire feed stock. In a crude sense, if you see, you have a wire, when you heat the wire, it changes into small droplets. So, these droplets are nothing but, for analogy sake, you can call it as powder. The wire, when you apply heat, it melts. So, when it melts, it finds into small droplets. So, these droplets, whatever we see, are nothing but powders. You can either call wire converted into powder, or we can directly take powder. This powder can be metal, the powder can be ceramic. Okay. The powder can also be polymer, why not? Although this basic approach can work for polymer, ceramic and metal matrix composite, it is predominantly used for metal powder. Okay. When I say metal matrix composite, so metal is a matrix and you composite, you will have a reinforcement, and this reinforcement also will be basically in powder form. Okay. Thus, this technology is often referred to as metal deposition technology. To avoid limiting the reader's understanding to just metal building materials, however, we will refer to this category of the process as beam deposition processes. Beam deposition processes use some form of energy focused into a narrow region, a beam, which is used to heat a material that is being deposited. This is what I discussed in the introduction. Beam delivery process are not used to melt a material that is pre-laid in a powder bed, but are used to melt material as they are being deposited. Beam delivery system processes uses a focused heat source such as laser, electron, plasma arc to melt the feedstock material. A feedstock material is a wire here, material, and built up a three-dimensional object in a manner similar to the extrusion based processes. Each pass of the beam delivery head creates a track of solidified material, and adjacent line of material makes up the layer. A complex 3D geometry requires either support material or a multi-axis deposition head. Supporting material is very important if you have free form or free hanging structures. A schematic representation of beam delivery process using powder feedstock material and laser is shown in the next slide. Most commercial beam delivery processes enable complete melting of the powder using a focused high power laser beam as a heat source. Research variants include using an electron beam or plasma source in the place of laser beam, or use a thin metal wire instead of powder as a building material. See, the advantage of electron beam is more focused, but the disadvantage is it needs vacuum. Today we talk about low pressure or low vacuum systems for developing, and today electron beam is competing with laser beam in this beam delivery system in the rapid manufacturing way. If you look at it, this is a powder feed nozzle. We have two powder feed nozzles. So, and then you have a lens which comes. Suppose you try to take a powder as you can take a polymer powder, you can take a metal powder, you can take a ceramic powder, and generally ceramic needs a very high power. So, what we do is we try to have the ceramics which will not melt, but the metal will melt and the ceramic gets embedded into the liquid metal, and then it forms a composite. So, it is very clear. You can see here you can have multiple nozzles and feeding the powder, and then you have a laser which is in the center which exactly focuses it and then melts it. So, you will have an optic system in between. In the schematic diagram we do not show, and this is called as a galvo stage, which swings and sweeps to get the XY plane data. And here you can see these are the track widths. The track widths, it is pretty interesting. You can see the direction of the track widths also changes. So, it is 0 orientation, this is 90 orientation, maybe you can have 45 orientation, whatever it is, and we can start building up the product. And here, since it is made out of metal, it can be used for as a real time usage, or this part which comes out is an example for rapid manufacturing. In many ways, BD techniques can be used as an identical manner to laser cladding and plasma welding machines. For the purpose of this discussion or a chapter, however, BD machines are considered as those which are designed to create depositions of complex 3D directly from CAD files rather than traditional welding or cladding techniques, which were designed for repairing, joining or applying coatings and do not typically use 3D data as an input format. The number of organizations that develop BD machines using laser and powder feeder are there are a number of organizations. So, the machines can be referred as lens, direct light fabrication, direct metal deposition, 3D cladding, laser generation, laser based metal deposition, laser freeform fabrication, laser direct casting, laser cast, laser consolidation, lace form and others. So, these are some of the machines and the techniques which are available today under the category of beam delivery system. Although the general approach is the same, differences between these machines commonly include changes in the laser power, laser spot size, laser type, powder delivery method, inert gas delivery method, feedback control scheme and or type of motion control utilized. Motion control is that belt drive, lead screw, whatever it is. Because these processes all involve deposition, melting and solidification of powder material using a traveling melt pool. Deposition, melting, traveling melt pool. That means to say it is not a pool at one point, the pool keeps traveling. That means to say as and when the laser keeps moving, it is trying to melt powder and it is going to take it along. Traveling the melt pool, the resulting path attain a high density because all the metal powders are now melt. So, it will all be in a pool form. So, it will have high density during the building process and porosity will be reduced. As the most common type of beam deposition system is powder based laser deposition system optimized for metal, a typical laser based melt deposition LBMD process can be mentioned as the paradigm process. In LBMD, a deposition head is utilized to deposit material onto the substrate. So, here it is interesting, you have a substrate, you can allow metal to be deposited. It is like laser rework you can say, or laser deposition you can say, and what you have done is you can have functionally graded materials on top. So, you can have multiple materials and this is the substrate. Okay. So, in LBMD, a deposition head is utilized to deposit material onto the substrate. A deposition head is typically an integrated collection of laser optics, powder nozzle, inert gas tubing and in some cases sensors. The laser optics is very important because the laser optics is not the ordinary optics, you have to do a coating. This coating should withstand the laser power and the laser light passes through this optics and then it tries to hit at the substrate. Powder nozzle is also a challenge. Feeding powder at the exact space at the required pressure is also a huge challenge. And when you try to flow powder, there is always a problem of agglomeration or clogging of the nozzle, then it leads to defects. In order to overcome this, we always try to use inert gas tubing. This inert gas tubing helps in pressurizing as well as forming a jacket on top of it such that the oxidation does not happen. And in some cases, it is also used as sensing. The substrates can either be flat plates or with a new part will be fabricated or an existing part on which the additional geometry will be added. So, this is what I said here. So, you can see here one material, you can see the second material. You can see two different materials. So, you can have functionally graded materials there. So, it is used for laser cladding or laser deposition. So, the figure clearly says this is a substrate, here it is flat and then you have a deposited material. See, these deposited materials flow through these two orifices. So, it comes at a pressure. So, when the particle comes, it comes in along the axis, it tries to meet and it tries melting at this point. When it starts melting at this point, it slowly gets deposited. So, you can have the powder coming from this powders can be polymer again, it can be ceramic, it can be metal. And when we talk about metal, it can be alloyed metal or it can be also a metal reinforced powder. So, this can come through and it can hit at the laser tip and it can start melting. So, a powder which comes and when this powder melts, it is definitely it will, when it reacts with the atmosphere, it is going to form compounds. Say for example, you have carbon rich, you have nitrogen rich, you have oxygen rich atmosphere around. So, the powder whatever is there in the molten condition where the diffusion can happen very fast. So, it can form carbides or it can form a ceramic material on top of it which might functionally degrade or which might deteriorate the usage of this part in real time. So, whatever gets generated from here, it is directly used as a final product for usage. So, here this air which comes here, shielding gas, this gas is basically purges or it tries to create an atmosphere around. This atmosphere tries to protect the liquid pool from getting reacted with the atmosphere and form these compounds or ceramic materials. So, it is very interesting. Today we can make aircraft parts by this process. We can make lot of biomedical parts through this process. We can make lot of automotive parts through this process. So, you decide what is the substrate, you decide the laser power, and you decide the powder which is to be deposited. Today, we have a huge application using this process. Okay. So, this process is called as laser based metal deposition process. And this is also interesting. If you want to do dye correction, if you want to do a dye correction, if there is a worn out dye, you want to add material, do some correction, and then you want to do some gouging process to remove the excess material, you can use this process and get it done. The deposition is controlled by relative differential motion between the substrate and the deposition head. This differential motion is accomplished by moving the deposition head, by moving the substrate, or by combining the substrate and the deposition head. See, it is interesting. If you want, you can try, if you want a flat surface, you can either move the laser, or the laser can be moved, or the table can be moved. The laser can be moved or the table can be moved. But if you move both, what you get is a taper. You can, so what I am trying to say is, you can also try to have multiple shapes, free-form shapes, by deciding the movement alone. And today the technology has gone so high, the laser head is attached with a CNC 5-axis machine. So, it can create any free-form surfaces and it can deposit. This differential motion is accomplished by moving the deposition head, by moving the substrate, or by combination of substrate and the deposition head motion. A 3-axis system whereby the deposition occurs in a vertical manner are typical. However, 4 or 5-axis system uses either rotary table or robotic arm are also available today. The kinetic energy of the powder particle being fed into the melt pool is greater than the effect of gravity on these powder during the flight. Understand this point, this is very important. The kinetic energy of the powder particle being fed into the metal pool is greater than the effect of gravity on these powders during flight. Okay. So, this makes sure that it does not create, see, there is a buoyancy which comes. Because of this buoyancy in the melt pool, there is a buoyancy, there is a density difference, so the material can be moved out. But on top of it, the kinetic energy of the powder particle just goes, hits it, and then starts moving it. As a result, non-vertical deposition is just as effective as vertical deposition. Very important point. Multi-axis deposition head motion is therefore possible as indeed quite useful. So, that means to say, if you see a nozzle, you will have holes. So, there are 4 holes here. So, from each of the holes you can start feeding different powders, and this can hit at the surface. So, this is one way, or the other way around is you can have multiple axis deposition heads are this is. In particular, if the substrate is very large and or very heavy, it is easier to accurately control the motion of the deposition head than the substrate. Conversely, if the substrate is a simple flat plate, it is easier to move the substrate than the deposition head. Thus, depending on the geometry's desire and whether new parts will be fabricated onto the flat plate or new geometries will be added to the existing part, the optimum design of LBMD apparatus will change. Design of the machine will change. The LBMD, the laser generates a small molten pool on the substrate as powder is injected into the pool. The powder is melted as it enters the pool. The powder enters the pool is what? At the pool you will have a laser which is getting focused. What is pool? Pool is a melt, whatever it is, and solidifies as the laser beam moves away instantaneously. Under such conditions, the powder can be melted during flight. That means to say, before dropping, during the flight itself, the powder can melt. Why does the powder melt? Because the surface area is large, the volume is too less, so it can easily melt. Okay. So, during flight and arrives at the substrate in the molten state. However, this is typically, and a normal procedure is to use process parameters that melt the substrate and powder as they enter into the melt pool. A typical small molten pool and relatively rapid traverse speed combine to produce very high cooling rates and large thermal gradients. Rapid traverse speed combine to produce very high cooling rates. So, gradients are created. These gradients are disaster. You should try to avoid having large thermal gradients, because if you have large thermal gradients, it is going to warp the surface. You are going to get, instead of a flat plate, you will get something like a warped plate. Okay. This is flat and this is warp. Instead of this, you will get a warped plate. So, large thermal gradient should be avoided. So, for this what we do is we try to do the entire exercise or the product development in an ambience where the temperature is maintained at a certain level, so that the thermal gradient is avoided. Depending upon the material or the alloy being deposited, these high cooling rates can produce unique solidification grain structure and or non-equilibrium grain structure, which are not possible using the traditional process. So, we know by extracting the heat, you can try to dictate the grain structure. If you extract it in if you extract it in different directions, or if you can control the extraction of heat, you are controlling the grain structure. You can create columnar grains, you can create small axial grains, uniaxial grains, or equiaxial grains you can try to create, and this dictates the final property. So, by doing this, we can also try to create unique solidification grain structures or non-equilibrium grain structures, the grain structures which you could never ever think about in the normal convention process you can do. Why are these grain structures very important? They play a very important role in creating toughness property, in creating hardness property, or a trade-off. At lower cooling rates, the grain features grow and look like a cast grain structure. The passing of the beam creates a thin track of solidified metal deposited on and welded to the layer below. A layer is generated by a number of consequent overlapping tracks. Okay. So, what we are talking about, these are the tracks. Several of these tracks forms a layer. These are the tracks and these are the layers. Okay. These are tracks and the entire thing is a layer. The amount of track overlap is typically 25%. So, what are we talking about? One track is typically 25%. So, this helps you to stretch in the tracks. So, this is 25% overlap, okay, of the track width, and typical layer thickness employed are 0.25 to 0.5 millimeter. After each layer is formed, the deposition head moves away from the substrate by one layer thickness. Powder feeding is a very challenging task. Powder feeding, because the powder are smaller in size, so they can easily fly off, they can easily get agglomerated. When it agglomerates, it clogs. So, powder feeding is a huge challenge, and if you have multiple different varieties of powders falling, the flow rate between them has to be controlled. The beam delivery processes can utilize both powder and wire stock feeding, like FDM process, wire stock feeding. Each has a limitation and drawback with respect to each other. The powder is the most versatile feedstock, and most metal and ceramic materials are readily available in powder form, because you do atomization. Metal you melt and atomize, like how do you spray the injection nozzle in your cylinder. So, like that you can also try to atomize and get metal powders. However, not all powders is captured in the melt pool. So, excess powder is utilized, and care must be taken to ensure that the excess powder is recaptured and clean state if recycle is required. So, that means to say, all this, if you dump lot of powder, it is need not that all of them will be melted. So, you will have only a track, along the track it melts, and rest of the powders should be removed, so that it can be used for melting. Excess powder feeding, however, is not necessarily a negative attribute, as it makes beam delivery process geometrically flexible and forgiving. This is due to the fact that excess powder flow enables the melt pool size to dynamically change. So, excess powder flow dynamically changes the melt pool. When you dynamically change the melt pool, you do not know whether you get a larger track or a smaller track. As described below, beam delivery process using powder feeding can enable overlapping scan lines to be used without the swelling or overfeeding problem inherited in the extrusion based processes. This is the advantage of BD system with EP system. EP is extrusion based processes. So, powder feeding. So, if you see that, so this is the shielded nozzle, this is the laser beam, and when the laser beam, you are feeding the powder from here. So, powder melts and it gets deposited. So, this is a substrate, and powder feeding position, you can see this is at an angle A. A is the powder delivery angle, this is one, and D is the powder nozzle standoff distance. This is a standoff distance. Interestingly, standoff distance, generally when you speak it is vertical, but here you will have at an angle. So, this is D, and the nozzle delivery angle is A. In BD, the energy density of the beam must be above a critical amount to form a melt pool on the surface. So, it depends on the laser beam power. Laser beam, because melting, it has to help in melting. When the laser is focused on a small laser spot, flux density increases. There is a region above and below the focal plane where the laser energy density is high enough to form a melt pool. This region is labeled in the figure. Okay, we will see the figure. So, what are we talking about? This is the laser beam, and in the laser beam, this is the waist, this is the beam waist, and this is what above and below the focal plane. We have a small area, but this Z will be too small, will be in few millimeters. Okay. So, here the region above and below the focal plane where the laser energy is high enough to melt the melt pool. This okay. If the substrate surface is either too far above or too far below the focal plane, no melting will happen. So, if it is above this or below this, no melting will happen. Similarly, the melt pool will not grow to a height that moves the surface of the melting pool outside the region. So, this is what we were trying to talk about. So, here is focus optics. So, that laser beam comes from here. So, you put an optics, So, the optics, they converge. So, here is this is the buried spot region, this is the exposed spot region, this is the spot. So, from here to here, this is a critical beam energy density for melting this, and this is, as I told you, this will be few millimeters. Okay. So, you can move up and down. Suppose you move less than this or above this, you will always have a defocusing. This defocusing will not help you to melt the material. it will just try to allow you to heat. If you are smart, we can use this for heating down the layer such that the temperature gradient is not created much and you can start joining with the previous layer. So, here it is very clear, it is left to you to play with the optics and the focal plane distance to get a proper melt. Within this critical beam energy density region, the height and the volume of the deposited melt pool is dependent upon melt pool location with respect to the focal plane, scanning rate, laser power, laser flow rate and surface morphology. Thus, for a given set of parameters, the deposit height approaches the layer thickness offset value only after a number of layer deposition. It is evident, for instance, in the figure where a constant layer thickness of 200 millimeters was used as a deposition head Z offset for each layer. The substrate was initially located within the buried spot region. So, let us go back and see the buried spot region, but no far enough within it to achieve the desired thickness for the layered show as a layer shown. Thus, depositing thickness approach the layer thickness Z offset as the spot becomes effectively more buried during each subsequent layer addition. However, too few layers were deposited to reach the steady state layer thickness value. If the laser and the scanning parameter setting used are inherently incapable of producing a deposit thickness at least as thick as the layer thickness of Z offset value, subsequent layer will become thinner and thinner. To be noted, if the laser and the scanning parameter setting used as inherently incapable of producing a deposit thickness at least as thick as the layer thickness Z offset value, subsequent layer will become thinner and thinner. Eventually, no deposit will occur when scanning for the next layer starts outside the critical energy density region. In practice, when the first layer is formed on the substrate, the laser focal plane is typically buried below the surface of the substrate approximately 1 millimeter, buried below. So, we are just trying to play with the height, make sure between two layers there is proper enough of gradient, melt pool happens on the top and heating happens on the bottom, and when the next layer comes there is a shift in the layer. In this way, a portion of the substrate material is melted and becomes a part of the melt pool. The first layer in this case will be made up to the mixture of melted substrate combined with the material from the powder feeder. So, one place it is all molten, now a new powder is hitting. So, with the material from the powder feeder, this is powder feeder, this is molten material, powder feeder, and the amount of material added to the surface for the first layer is dependent upon process parameters and focal plane location with respect to the substrate surface. If little mixing of the substrate and deposited material is desired, then the focal plane should be placed at or above the substrate surface to minimize melting of the substrate, resulting in the melting pool made up almost entirely of the powdered material. So, it is just playing with the focal plane and depositing layer. So, what happens when the laser hits the powder? It creates a melt pool. So, now there is a liquid metal. So, in this liquid metal, when you try to add material, that is what is we are talking about. If little mixing of the substrate and the deposited material is desired, like in laser cladding, then the focal plane should be placed at or above the substrate surface to minimize melting of the substrate, resulting in a melt pool made up of almost entirely with the powder material. The powder is typically fed by first fluidizing a container of powder material and then using a pressure drop to transfer the fluidized powder from the container to the laser head through the tubing. So, when you start flowing the powder, it is not necessary the powder should keep flowing because of gravity. So, here you have to create a pressure drop so that the powder flows properly and it hits at the liquid metal. The powder is focused at the substrate laser interaction zone using a coaxial feeding, 4 nozzle feeding or a single nozzle feeding. Coaxial means it has multiple axes. Around the axis there are multiple feeding points, coaxial feeding and 4 nozzle feeding and a single nozzle feeding. In the case of coaxial feeding, the powder is introduced as a toroid surrounding the laser beam, which is focused to a small laser spot using shielding gas flow as illustrated in the next figure. So, this is what it is. So, you can see a coaxial feed, this is coaxial and B is single nozzle. So, this is single nozzle. So, you can see here these are shielding gases which come and here are powders which come. Powders can be same powder, powders can be alloy powder. So, whatever it is you can do it, no issues. So, this is a diagram which talks about coaxial feeding, this is talking about a single axial nozzle feeding. The powder feeder, the two main benefits of coaxial feeding are that it enables a higher capture efficiency of the powder. The focusing shielding gas can protect the melt pool from oxidation when deposited in the presence of air. The single nozzle feeding involves a single nozzle point at the interaction zone between the laser and the substrate. The main benefit of a single nozzle feeding are the apparatus simplicity, a better powder capture efficiency than 4 nozzle feeding, the ability to deposit material into tight locations. So, these are some of the advantages of single nozzle feeding and as compared to that of coaxial feeding. A 4 nozzle feed involves 4 separate nozzle heads equally spaced at 90 degrees increment around the laser beam. So, it is something like this. Focus to intersect at the melt pool. These are all nozzle feeding. The main benefit of 4 nozzle feeding system is that the flow characteristics of 4 nozzle feed gives more consistency in building height of complex and arbitrary 3D geometries that involve a combination of thick and thin layers. So, and if you see interestingly, all the product which are produced out of this process is directly used for application. When you use metals, it directly gets, for example, people make crown which is put on top of a teeth directly through this process. People make implants through this process. People directly make dye repair through this process. People make small micro channels for microfluidic applications or for heat exchangers through this process. People make medical devices through this process. Okay. So, lot of interesting things are coming out. In the case of wire feeding, the volume of the deposit is always the volume of the wire that has been fed, and here is 100% feedstock capture efficiency, which is not there in the powder form. This is effective for simple geometries, coating of surfaces and or deposits where porosity is acceptable. Simple geometry, coating of surfaces and or deposits where porosity is acceptable. However, when complex, large and fully dense parts are desired, geometry related process parameters must be carefully controlled to achieve a proper deposit size and shape. Just in extrusion based process, large deposits with geometric complexity must have porosity designed into them to remain geometrically accurate. For certain geometries, it is not possible to control the geometric related process parameters accurately enough to achieve both high accuracy and low porosity with wire feeding unless periodic subtractive processes is done. So, that means to say you deposit and then you have a milling cutter which rotates and cuts. So, you have deposited on top of a surface, this is a milling cutter. So, this cutter after deposition comes here, machines it, removes the undulation on the surface and allow the next drop to come in. So, it is done to rest the geometry in the state. Thus, the selection of wire feeding system versus powder feeding system is best done after determining what type of deposit geometries are required, whether a subtractive milling system will be integrated with the additive process head. This is if cannot be done, so to go for powder. If milling along with the wire feed, if you can integrate a milling cutter, then look for such systems. So, wire feed. So, this is the wire which is getting fed. It looks like your MIG system and TIG system. So, this is a wire feeding coming up. Here is a laser. So, this laser or the electron beam, so it comes and hits at the pool, and here it melts. Here is a melt pool we talk about. So, this is the molten, they call it as puddle, we will call it as melt pool. So, this is the wire coming here, electron beam can be replaced by laser. So, this is done prior, that means to say before it is, now it is moving, so it is deposited prior, and here is a substrate. If you want to have cladding, metal cladding, then this process can be effectively used for doing it. So, here is resolidified alloy. So, this is at the bottom. So, you can get it done. So, here is electron beam for you which can do the process. This is the direction motion. You can move the part, you can move the electron beam, you can move both also to get the required output. So, here is a typical BD system. So, this is how the entire system looks like, and you have the CAD is fed here. So, the CAD is converted. So, CAD to STL, STL to layer, layer to part to post process is done in this machine. So, CAD, STL, layer cutting is done, and then it is fed to the machine. The part geometry is getting developed in this machine. So, where we use metal wire for, or a wire feeder for doing it. In the typical BD system, an oxygen removal or a gas recirculation system is used to keep the oxygen concentration in the gas nearly below to 10 ppm oxygen. The inert gas chamber, the laser type 4 nozzle feeding design utilized by Optomech makes the lens machine. Lens is expanded as laser engineered net shaping or near net shaping. People also call it as near net shaping or net shaping. Okay, lens machine, some of the most flexible platforms for BD. As many materials can be effectively processed with this combination of laser type and atmospheric condition. Most lens machines are 3-axis and do not use a closed loop feedback control. However, Optomech now offers 5-axis laser wrist, so which has all freedoms. When we talk about 5-axis, you have rolling motion, pitching motion and yawing motion. So, this will try to give you all possible orientations so that you can develop the object and get it. That can enable deposition from an orientation, and systems for monitoring built height and melt pool area can be used to dynamically change process parameters to maintain constant deposition characteristics. As BD technologies become accepted in the aerospace industry, a similar system will likely become commercialized again. The benefit behind adding features to simple shapes to form aerospace and other structures will, with an otherwise poor buy to fly ratio, makes sense. So, now what is happening? Very complex geometry can be easily made through using this lens process or this beam delivery process, direct metal. So, now you can see GE or Airbus claiming themselves they have reduced the weight of the machine by 30%. They have ramped up their production rate by 30% because of this rapid manufacturing machines coming into existence. The term buy to fly refers to amount of wrought materials that is purchased as a block that is required to form a complex part is called as buy to fly. The amount of wrought materials that is purchased as a block, then you try to do a subtractive process and then try to make a complex shape. In many cases 80% or more of the material is machined away to provide a stiff, lightweight frame for the aerospace structure. This is what happens with aluminum alloys for frames. We remove 80% of the material. So, now by using this beam delivery system direct deposition, we can try to make energy efficient aerospace materials. So, this is a metal satellite housing built with a hybrid process is shown. The base was machined from billet stock and the thin wall structures were added with the lens DED process. So, thin wall structure, this is all done by lens. These are thin wall structures. So, process parameter, unlike SLA, FDM, SLS, which comes pre-programmed with an optimized process parameters for materials sold by the machine vendor, BD process are sold as flexible platforms. Thus, BD users must identify the correct process parameter for their application. Optimum process parameters are material dependent, application geometry dependent. Important process parameters are track scan spacing, powder feed rate, laser traverse, laser power and laser spot size. The powder feeder rate, laser power, traverse speed are interrelated. For instance, an increase in the feed rate has a similar effect to lower the laser power. So, these two are interrelated, so you should be careful. Likewise, increasing the laser power or powder feed rate and decreasing the traverse speed all increases deposition thickness. So, you have to make a trade off between this. From an energy standpoint of view, as the scanning speed is increased, the input laser energy decreases because shorter laser dwell time resulting in smaller melt pools of the substrate and more rapid cooling. So, basically when you quickly scan, it is going to be fast movement, laser interacting with the material is less. So, low amount of energy is applied on the surface, low melt pool. So, this will try to give you thin layers or it might produce defects. The scanning pattern also plays a very important role as far as the quality of the product. It may be desirable to change the scanning orientation from layer to layer to minimize the residual stress built in. So, that is why you see we saw earlier itself 0 degrees, 90 degrees, 45 degrees orientation. The track width hatch spacing must be set to so that the adjacent beading overlaps and the laser thickness setting must be less than the melt pool depth to produce fully dense products. Sophisticated accessories equipments for melt pool imaging and real-time deposition height measurement have been developed. What is the reaction or what is the temperature at the melt pool? Because if there is more amount of melt pool, so this is going to create more amount of melting and solidification, and we have to now balance it up. And the other thing is, all the melt, whatever happens when it solidifies, it does not give you uniform height thickness. So, we need to measure the melt pool temperature using imaging techniques and measure the real time height, so that we know what is the flow of the powder to be given. It is possible to monitor the melt pool size, shape and temperature to maintain the desired pool characteristics. The pool characteristics is directly proportional to the defect. To control deposition thickness, travel speed can be dynamically changed based upon the sensor feedback. Similar to the control solidification rate, the microstructure and the properties also changes. Part produced in beam deposition process exhibit cast microstructure, that means to say columnar, equiaxial, whatever. The processing condition influence the solidification microstructure in way that can be predicted in part by rapid solidification theory. Grain engineering is a new latest topic which is in the research front. People have identified, if I start doing engineering on the grain size distribution, grain shape, I can dictate the material property. For a specific material, solidification microstructure essentially depends on the local solidification condition, especially the solidification rate and the temperature gradient at the solid liquid interface. By calculating the solidification rate and the thermal gradient, we can try to predict or play with the microstructure. For better understanding of microstructure in beam deposition process, Booth and Gingley have developed a procedure for calculating thermal gradient G and solidification rate R analytically and numerically. So, there is a factor called as G factor and R factor, thermal gradient and solidification rate. Okay. The calculated G and R values can be plotted on solidification map to determine the type of microstructure which can be achieved with different beam deposition equipments, process parameter and material composition. This dictates the quality of the product. The solution of both thin wall and bulk deposition has been described. For brevet sake, a later work of Bonath et al. Based upon the 3D Rosenthal solution for a moving point heat source on an infinite substrate will be introduced here. So, this is what is the Rosenthal effect. So, Rosenthal geometry is there. This is a laser beam, it moves at a velocity v. So, at x plane, y plane, z plane, here is the alpha and q, heat and the thermal conductivity. The simplest model, material deposition, is ignored. The model considers only heat conduction with a melt pool. There is convection and radiation, but we take only conduction and substrate due to the travel heat source moving with a velocity of v. The fraction of the impingement energy absorbed is alpha q, which is a simplification of the physical complex temperature dependent absorption of the laser by region of melt pool and solidification absorption of energy by powder in flight and other factors. This is very important. See, when we talk about laser interacting with material, we have absorption and then we have reflection, we have transmission. The laser, when it interacts with material, it can undergo anything, it can absorb, it can reflect or it can transmit and go. So, we have to find out what is the ratio, and this absorbivity, the light interaction absorbivity, it depends from material to material, it is not a constant, and also it depends on the wavelength of the laser. So, thus a single parameter A represents the fraction of impinging laser beam powered absorption. Beam delivery process are capable of producing fully dense part with highly controllable microstructure. This process can produce functionally graded components in the x and y z direction. The main limitation of the beam deposition process are poor resolution and surface finish. The accuracies which we talk about is 0.25 millimeter surface roughness of less than 25 millimeter are difficult for this process. The benefits and the drawbacks: slower build speed is another limitation. Building time can vary very long for these processes, 25 to 40 grams per hour. To achieve better accuracy, small beam size and deposition rates are required. Conversely, to achieve rapid solidification rate, degradation of the solution and the surface finish results. Change in the laser power and scanning rates to achieve better accuracies. Deposition rates may also affect the microstructure of the deposited compound, and thus finding an optimum deposition condition necessitates trade-off between the build speed, accuracy and the microstructure. The examples of unique capabilities of beam deposition includes beam deposition offers. I have been using mixedly using beam deposition or beam delivery. Please try to have. So, I have also talked about beam delivery. Okay. So, this is all beam deposition or beam delivery, but I would like to stick on to the word beam deposition. Beam deposition offers the capability of unparalleled control of microstructure, the ability to change material composition and solidification rates by simply changing the powder feed. So, this is what is the two terminologies, thermal gradient and R I was using, solidification rate. For process planning gives designer and researchers a tremendous freedom. The BD is capable of producing directionally solidified and a single crystal structure. BD can be utilized for effectively repairing and refurbishing defective and service damaged high technology components such as turbine blades can be worked about. As a result of the combined strength of beam deposition process, practitioners of beam deposition primarily fall into one of the several categories. The first category is they have been highly utilized by research organization interested in development of new material alloys and the application of new or advanced material to industry. They have used it. Second, they have found a greater success in facilities that focus on repair, overhauling and modernization of metallic structures. So, the people can fall in this category. The third category is for adding features or materials to the existing structure to improve their performance and characteristics. So, these are the three places where people fall when they wanted to use this beam deposition process. In this third category, beam can be used to improve the life of the injection molding or die casting die by depositing wear resistance alloys in high wear locations. It is being actively researched by multiple biomedical companies for improving the characteristics of biomedical implants. It is being used to extend to wear characteristics of everything from driving shaft to motorcycle engineering components is used. Finally, to conclude, to recapitulate what we have seen in this lecture, what is the material delivery in BD? Describe briefly general beam deposition process description, explain powder feeding and wire feeding, describe BD systems. So, these are some of the things which we saw in this lecture. Thank you.